resistance to flow in rough pipes is equal to the head loss in rough pipes, right? Because there's going to be friction in rough pipes. So what we're going to do is to determine this head loss as a result of the resistance to flow in rough pipes. Doing so is possible by having a length of a pipe and also by having two pressure gauges at cross-section 1, cross-section input, and cross-section output, or cross-section 2. And you can see the control volume is the red polygon in the pipe. So we are going to write down our energy equation between section 1 input and section 2 output, and then see if we can find this head loss based on the energy equation. So what I'm going to do is simply write the energy equation that you are familiar with. I'm going to add alpha, which is the velocity correction factor. If you have any pump, it would be on the left-hand side of the equation. And the right-hand side of the equation is very similar to the left-hand side, but for the output cross-section. Again, I'm going to add alpha. If you have any turbines, it would be over here. And also your head loss is over here too. We know that our head loss is equal to HF, major head loss or pipe head loss or friction head loss, because we don't have any fixings. We don't have any valves or Y-junction or any fixings in this short length of the pipe. Now, let's see if we can simplify this. Based on continuity equation, we already know that velocity in is equal to velocity out, right? Because the diameter of the pipe is the same thing and flow is steady. So we can simply say that these two terms cancel each other out, right? Now, also, we know that there is no pump in our control volume, so this would be 0. There is no turbine in our control volume, so this would be 0 as well. Now, I can rewrite this equation down here. It would be pressure head of input plus elevation head of input is equal to pressure head of output plus elevation head of output plus HF. Right? Okay. And now HF could be written as pressure head of output minus pressure head of input All right, so the term in brackets is piezometric head, right? Now, I can write piezometric head in terms of piezometric pressure. So what I'm going to do is multiply gamma, or specific weight, to two sides of the equation. So if I do that, the result would be gamma HF is equal to P out plus gamma Z out minus P in plus gamma Z in. Okay, so this term now is piezometric pressure for the outlet section, and this term is piezometric pressure for inlet section, right? So what I can do is write HF to be piezometric pressure for outlet section minus piezometric pressure for inlet section divided by gamma of the fluid. And this is how you calculate HF when you have two pressure gauges at the beginning of your control volume and at the end of your control volume. Now, you are going to ask me that, well, in reality, how many pressure gauges can we have in a real system with a very, very long pipe? And you're 100% correct. This is not feasible because we cannot have many pressure gauges installed in a pipe, right? In reality, it's not feasible. So this method of finding HF would be good in laboratory when you have a short length of pipe and you can put many pressure gauges in, but it's not going to work in the field. So we need to have some alternative method to calculate HF or to calculate resistance to flow, in other words, head loss in a pipe. And that alternative method is an equation called Darcy-Weisbach method. So it is spelled like this: Darcy-Weisbach method or equation. This Darcy-Weisbach equation allows you to calculate HF for laminar and for turbulent flow using velocity of the flow that can be measured, length of the pipe, and diameter of the pipe. So much easier to measure, right? This equation can be developed for laminar flow and turbulent flow. So it is very versatile, and you can use it for any type of flow that you have. In next slide, I'm going to go over derivation of Darcy-Weisbach equation and how you can calculate HF based on characteristics of the pipe. In this slide, what I'm going to do is to derive Darcy-Weisbach equation for a round pipe, for round pipes. Perfect. So as you can see, we have a pipe on the left-hand side photo, and we have selected the control volume. The pipe is angled, and the angle is alpha over here. The control volume is a cylindrical shaped control volume with the length of delta L and diameter of D. There are two directions that we have selected. S direction is parallel to the center line of the pipe, and R direction is radius direction. Now, we are going to single out the control volume and put all the forces that are acting on the control volume on it. We're going to start with pressure forces because they are the most obvious forces. Left-hand side pressure force would be P sub 1, or pressure at section 1 times cross-sectional area of the cylinder, and P sub 2A is pressure force at section 2, or the right end of the cylinder. Another force that we need to consider is shear stress force, this force basically. This force is as a result of the friction between the walls of the pipe and the fluid. And shear stress force is equal to shear stress, tau 0, times surface area of the cylinder. And you might ask, how do we calculate surface area of the cylinder? It's easy. It would be the circumference of the circle times length of the cylinder. So if I want to write A would be equal to pi times D, which is the circumference of the circle, times delta L, right? And as a result of this, then the force, the shear stress force, or F shear, would be equal to, I will write it over here, tau 0 times pi times D times delta L. Perfect. The other force that is acting on this control volume is weight. And because our cylinder is angled, then we will have two components for weight. One component would be in the direction of S direction, which would be W sine of alpha. And the other component is this component, which is W cosine of alpha. Perfect. Now we have all forces. Whenever forces are involved, and in order to derive Darcy-Weisbach equation for round pipes, we need to write momentum equation. I've already written momentum equation in S direction for you. Now let's analyze momentum equation term by term. The first term on the right-hand side of the equation is changes of mass of control volume times velocity of control volume over t, over changes of time. Since the mass of control volume does not change over time, and the velocity of control volume does not change over time because our flow is steady, then this term is 0. Also, because the diameter of the pipe is constant, then the velocity at section input, or section 1, is equal to the velocity at section output, or O, or section 2. Then these two terms cancel each other out. So in other words, what we have is summation of forces in S direction is equal to 0. So the only thing that I need to do is to write down the force equilibrium and see if I can find HF or head loss, and that would be my Darcy-Weisbach equation. So let's write down all the forces that are acting on this control volume. The first type of force, as I told you, is pressure force, so F pressure. The other type of force would be force as a result of shear stress, and because the direction of shear stress force is opposite direction of positive S direction, I'm going to include a negative sign, F shear, and then minus F weight. Why negative sign? Because W sine of alpha has the opposite direction of positive S direction, and this should be equal to 0. Just to remind you, this is our positive S direction. Perfect. Now that I have this equation, all the forces, I'm going to replace the value of forces in this equation. So pressure force, we have two pressure forces. I'm going to write them together. So it would be P1 minus P2, and then cross-sectional area of the cylinder, which would be pi divided by 4 diameter to the power 2. This is the pressure force. Minus shear stress force, I already calculated for you and written it for you. It would be tau 0, shear stress, pi diameter times delta L, minus weight force, and weight force would be, because, let me write it over here actually, I know that weight of the cylinder is equal to gamma times volume of the cylinder, right? So I can write down W over here. It would be gamma times volume would be cross-sectional area times delta L. So it would be pi divided by 4 times d to the power 2 times delta L. And I'm going to replace that and put it in the equation over here. So W would be gamma pi divided by 4 d to the power 2 delta L times sine of alpha, because we need the s direction version of weight. That is equal to 0. Perfect. So now I'm going to do a little bit of reorganization and write this equation in terms that are familiar to me. So this equation can be written as, I'm going to write pressure at section 1. You need to pay attention that we can replace sine of alpha with its equivalent. So take a look at this triangle over here. From trigonometry, you can conclude that sine of alpha is equal to delta z, in other words, z2 minus z1, divided by delta L, and delta L is simply the length of the cylinder, right? So when you replace that, then I can over here write plus gamma z1 minus P2 plus gamma z2 is equal to 4 delta L tau sub 0 divided by d. All right. This equation is based on reorganization of the force equilibrium that I've written for you. The reason that I have written this equation like this, because I already know these terms, right? These terms represent what? Represents piezometric pressure at section 1 and piezometric pressure at section 2, right? And I know that based on previous slide, I know that piezometric pressure at section 1 minus piezometric pressure at section 2 represents gamma times HF, gamma times head loss, right? So what I'm going to do right now is write the equation like this. So based on what we know over here, HF is equal to 4, instead of delta L, because that's the length of the cylinder, I'm just going to write L. And then tau sub 0 d gamma. Okay, so this is the equation that Darcy-Weisbach came up with. And in order to have this equation in terms that can be applied to laminar and turbulent flow, what they did is that they multiplied these variables by kinetic terms. Density, velocity to the power 2 divided by 2. Again, density, velocity to the power 2 divided by 2. So they multiplied this equation by this, and then they reorganized it. Again, reorganized it to come up with some familiar terms. So they came up, their reorganization, they came up with 3 brackets. The first bracket involved 4 shear stress divided by density, velocity to the power 2 divided by 2. The second bracket was simply length of cylinder divided by diameter. And the third bracket was velocity to the power 2 divided by 2g. All right, so they decided to call this term over here F, or friction factor. Okay, this term, friction factor, will take different values for laminar flow and for turbulent flow. But everything else, like length, like diameter, like velocity, you can easily calculate, right? So the only thing that you need to figure out when you are calculating head loss, or HF, pipe head loss, is friction factor. So they wrote down this equation in a general form, and they call it Darcy-Weisbach equation. So just to reiterate that equation, I'm going to write it once more and over here. So HF is equal to F, which is a friction factor, times L over D times velocity to the power 2 divided by 2g. This equation that I have written in red with using my red pen, this equation is called Darcy-Weisbach equation. And it can be used for both laminar and turbulent flow to calculate head loss. Now, we know about this equation. We need to find out how to calculate F, or friction factor, for different classifications of flow, and that would be the topic that I'm going to discuss from now on. Now that we have learned about Darcy-Weisbach equation, we can move ahead and calculate head loss and friction factor for different types of flow. And by that I mean laminar flow or turbulent flow. Right now in this slide, I'm going to focus on laminar flow. And everything that I'm explaining right now is covered actually in chapter 10, section 5 of your textbook. So the full derivation of head loss and friction factor for laminar flow can be found in section 10.5 of your textbook. You are encouraged to go and take a look at that, because here right now I'm just going to cover the main topics. I'm not going to go over details of derivation. So for laminar flow, you already know the velocity distribution, right? We have been talking about it a lot. Velocity distribution for a section of a pipe that has laminar flow would be something like this velocity distribution that you can see over here. Velocity changes with radius. When radius is equal to r sub 0 at the walls of the pipe, velocity is 0 because of no slip boundary condition. And at the beginnings, or on the center line of the pipe, velocity has maximum velocity, v sub max. Now, if I ask you what would be the equation for velocity that changes with radius, you would tell me that it has some kind of parabolic distribution. So if I want to write that mathematically, velocity that changes with the radius of the pipe would be equal to velocity max times r sub 0, radius of the pipe, minus r that changes from the center line of the pipe, divided by r sub 0 to the power 2 to make it parabolic, right? All right, so if you use this equation for velocity distribution and calculate average velocity, and then put that average velocity in energy equation, you will be able to calculate HF. You'll be able to find another equation for HF. So that's exactly what I want to do. I'm not going to show all the energy equation derivations of it, but here I will show you the final result. So if you put that average velocity into energy equation for this pipe again, your HF will be calculated as this. It would be 32 times mu, which is dynamic viscosity, times L times average velocity, which comes from the velocity distribution over here, and divided by gamma times d, or diameter, to the power 2. This would be the equation that you get. Now, this is HF. We also have HF based on Darcy-Weisbach equation. So if we make these two equations equal to each other, then we can calculate friction factor, right? And that's exactly what I'm trying to do. So I'm going to write this equation over here. It would be, again, 32 mu L average velocity, gamma diameter to the power 2, should be equal to HF calculated from Darcy-Weisbach. So F, L divided by D, velocity to the power 2, and again, average velocity, divided by 2g. So if you reorganize this equation and make it simplified, then you'll end up having F like this. So F, or friction factor, would be equal to, one term of it would be 32 mu times length times average velocity. I'm going to refer to average velocity as v, and divided by gamma times d to the power 2. And again, another term would be d divided by L. And finally, you will have 2g velocity 2. Now you can do some simplifications over here. This velocity cancels out with the power of this velocity. This diameter cancels out with the power of this d. L cancels out with this L. So I'm going to continue writing over here. F can be simplified and written as 64 times mu divided by density, d, and velocity. All right, so if you remember Reynolds number. Reynolds number could be, if you remember, I will write it over here as a reminder. Reynolds number for a pipe with diameter d can be calculated as rho velocity d divided by mu, right? So this is just as a reminder. Now, take a look at this term over here. This is simply 1 over Reynolds number, right? So I can tell that F, or friction factor for laminar flow, is equal to 64 divided by Reynolds number for a pipe with diameter d. All right, so now I found this F value, friction factor, for laminar flow. So now, in order to calculate head loss in a pipe that has laminar flow, I just need to calculate Reynolds number, calculate F, or friction factor, and then put that into the Darcy-Weisbach equation to be able to calculate head loss. Very easy, and this has an analytical solution, meaning that F can be directly calculated using Reynolds number. There's no need for trial and error, okay? Now, we're going to go over a couple of examples to make sure that this concept is clear. Example number 1, to make sure that you understand friction factor and also head loss. We have oil with specific gravity of 0.85 with a kinematic viscosity, or nu, of 6 times 10 to the power negative 4 meters squared divided by second. That flows in a 15 centimeter diameter pipe at a rate of 0.020 cubic meters per second. What is the head loss for a 100 meter length of pipe? Perfect. So the first thing that I'm going to do, because I have flow rates over here, is to calculate average velocity. And average velocity, or V, is simply Q, or flow rate, divided by area. So I am going to calculate that 0.020 cubic meters per second divided by the area, which is simply pi, times the diameter, which is 0.0 or 0.15 meters to the power 2 divided by 4. Pi should be divided by 4. There we go. And when you calculate this, your velocity would be equal to 1.13 meters per second. All right, this is the average velocity. Now, I have the average velocity. I'm going to calculate Reynolds number to figure out if the flow is laminar or turbulent. So I know that Reynolds number for a pipe with diameter of d is equal to rho velocity diameter divided by mu, or I can write it in terms of nu, velocity diameter. Why I can write it in terms of nu? Because what I have here is kinematic viscosity, and kinematic viscosity is equal to nu. Perfect. I calculated velocity to be 1.13 meters per second. Diameter is going to be 0.15 meters, and kinematic viscosity is 6 times 10 to the power negative 4 squared meters divided by second. Reynolds number, which is a non-dimensional number, would be equal to 283. So because 283 is less than 2000, I can conclude that my flow is laminar. All right, now because I have laminar flow, I can calculate friction factor, or F, using the laminar flow equation, which was 64 divided by Reynolds number. So I already calculated Reynolds number to be 283, and 64 is in the numerator. F, or friction factor, would be equal to 0.226. All right, I have the friction factor. I need to put it in Darcy-Weisbach equation. And Darcy-Weisbach equation can be written as H sub F, or head loss, is equal to F L divided by diameter times velocity squared divided by 2g. So F is 0.226. Length of the pipe is 100 meters. Diameter of the pipe is 0.15 meters times velocity squared would be 1.13 meters per second divided by 2 times 9.81. Now, if you calculate this, the value for HF would be 9.83 meters, and this value is your head loss. What kind of head loss? It's pipe head loss, or friction head loss, or major head loss. All right, so we know that in this situation, when we have oil, then if oil flows for 100 meters in a pipe that is 100 meters long, and the pipe is obviously rough, then over this 100 meter length pipe, we are going to 9.83 meters of head loss. And this head loss can be considered in your engineering design when you are designing a pipe to move something from point A to point B. Let's go over another example. We have a hydraulic apparatus, and it is important in this hydraulic apparatus that the flow of water remains laminar. So I'm going to circle laminar out because we want laminar flow. To be safe, we will require Reynolds number to be less than 1,500. What we are going to find is the maximum height of water above the outlet of whatever hydraulic apparatus that we have if the length of the pipe is 100 meters with a diameter of 4 millimeters. And also we have been given the value of kinematic viscosity, or nu. Just to make sure that we understand the problem, I'm going to sketch a schematic representation of what we have. So we have a reservoir that is connected to an outlet. An outlet is a pipe that has a length of 100 meters and diameters of 4 millimeters, or 0.004 meters. And the pipe is apparently a jet of water to the atmosphere. If this is the level of water, what you're going to find is delta Z, or the level of water above the outlet, in a way that the flow remains laminar. Okay, and we have been given a criteria in this to be safe. We are going to consider Reynolds number less than 1,500. So in other words, the maximum Reynolds number that we can have in this system is equal to 1,500. So the first thing that I'm going to do is write energy equation. That's because pressure is involved, velocity is involved. Writing energy equation is a good practice. So I'm going to select two sections. One section would be on the surface of water because I have information on it. The other section would be the outlet of this pipe over here, section 2. So writing energy equation on that would be Z1 plus, you already know all the terms over here. I'm gonna, because there is no pump and there is no turbine in the system, I'm not gonna write those. And alpha, velocity 1 to the power 2 divided by 2g. And terms for section 2. Plus there is going to be head loss as a result of the friction, so plus HF. Now, can we simplify this equation? Yes. Pressure at section 1 is equal to 0 because it's touching the atmosphere. Velocity of the surface of the tank is going to be 0 as well. Pressure at section 2 is going to be 0 as well. What else? One important, so velocity at section 2 is not going to be equal to 0, right? Because it's a jet of water. However, because we are going to consider laminar flow, alpha should be equal to 2. Remember that alpha for laminar flow is equal to 2. So this alpha over here would be equal to 2. And now we need to calculate HF as well. And we know that HF can be calculated using Darcy-Weisbach equation, which is F, L divided by D, and then velocity to the power 2 divided by 2g, right? All right, so in order to calculate F, or friction factor, we need Reynolds number. We know that the flow is laminar, so I'm going to use the equation for laminar flow for Reynolds number. Reynolds number, the maximum Reynolds number in which flow remains laminar is 1,500. So 1,500 over here and 64 in the numerator. F would be equal to 0.043. That's the value of F that we have. Now, we need to put this value into Darcy-Weisbach equation over here, right? However, we don't have the value of velocity, but that's not a big deal because we have Reynolds number. Reynolds number, which is equal to 1,500, is equal to velocity times diameter that I'm going to replace over here, 0.004 meters, divided by kinematic viscosity, 1 times 10 to the power negative 6 meters squared divided by second. As a result of this, velocity would be equal to 0.375 meters per second. Cool. Now we have velocity. We can calculate HF. HF is equal to F 0.043 times. What's the length of the pipe? Is 100 meters. What's the diameter of the pipe? It is 0.004 meters times velocity. We just calculated that, 0.375 meters per second squared, and then 2 times g. Perfect. Now, we can easily calculate this. I haven't calculated in my notes, but this can be calculated. We have all the values. Now, if I rewrite the energy equation, it would be delta Z, which I need to calculate, which is the value that I want, equals alpha velocity squared divided by 2g plus HF. HF is simply this HF that you can calculate from here. So it would be equal to, alpha is 2 times velocity is 0.375 to the power 2 divided by 2g plus HF. And if you calculate this, delta Z would be equal to 7.7 meters. All right, so this is the maximum delta Z that results in Reynolds number of 1,500. So if you want to have Reynolds number equal to 1,500, delta Z should be less than or equal to 7.7 meters to maintain a laminar flow. So now you can see that you can actually play with this simple scenario to have laminar flow, turbulent flow, and you have learned how to calculate head loss due to friction or major head loss in these kind of situations. All right, so far you have learned how to calculate friction factor, or F, for laminar flow. Now we're going to talk about turbulent flow. All right, so for laminar flow, velocity distribution was something like this, right? However, you already know that for turbulent flow, velocity distribution is not like that. It would be more like something like this, right? So we cannot use the velocity distribution equation that we use in derivation of friction factor for laminar flow, right? The velocity distribution would look like something like this. Velocity that changes with radius is equal to maximum velocity times radius of the pipe minus variable r that changes from the center line of the pipe divided by r0. This time, instead of when we had laminar flow, the power of this term in brackets was 2. This time, the power changes based on the roughness of the pipe, right? Now, so for different values of Reynolds number, this power, m, changes. So you can see that I have Reynolds number here, and m, which is the power of velocity distribution over here. As Reynolds number changes, you can see that m also changes as well. So the situation would be a little bit different here in turbulent flow than laminar flow. How is it going to be different? So F, or friction factor, was a function of Reynolds number for laminar flow. Now, for turbulent flow, the situation would be a little bit different. I'm going to write for turbulent flow, F is going to be a function of Reynolds number and also a relative roughness coefficient. So I'm going to write relative roughness coefficient. So whenever your flow is turbulent, F is not only a function of Reynolds number, but also a function of relative roughness coefficient, meaning that it matters if your pipe is made out of concrete or plastic or glass or whatever. Okay? Now, to do this, to calculate F for turbulent flow, you have a set of equations or you have a set of graphs. And these kind of graphs are called Moody diagram. So you need to use this Moody diagram to be able to locate the roughness of your pipe and also to be able to locate Reynolds number, and based on that, find friction factor. Now, having this in mind, we are going to move ahead and find this Moody diagram and learn about Moody diagram and different components of Moody diagram and see how we can find friction factor for turbulent flow. This figure is figure 10.14 of your textbook, which is Moody diagram. There are a couple of points that I want to make sure that you understand from this diagram. Number one, we are not going to use this axis of Moody diagram in this class. So just disregard this axis of Moody diagram. Number two, on the x-axis, you have Reynolds number for a specific diameter pipe. On your y-axis, left-hand side y-axis, you have friction factor F. And this is Darcy-Weisbach friction factor F. And on the right-hand side y-axis, you have a term called relative roughness. Remember that friction factor was a function of Reynolds and friction and relative roughness, right? This is your relative roughness. Relative roughness over here is K sub S divided by D. D is the diameter of the pipe. And K sub S is a term that is called equivalent sand grain roughness. So I'm going to write it over here. Sand grain roughness. The units for this is units of length, and the units of diameter is obviously units of length as well. So relative roughness is non-dimensional, and obviously Reynolds number is non-dimensional as well, right? So what we are going to do is whenever we have a pipe that is rough, that roughness is associated with one of these lines that you can see on your screen, one of the blue lines that you can see on your screen. So for example, if the relative roughness of your pipe is equal to 0.015 over here, you need to look for different values on this blue line that I'm going over. There we go. And once you found your relative roughness, you need to find Reynolds number. Finding Reynolds number on this diagram is a little bit tricky. Why? Let me tell you. So you can see that this line is equal to 10 to the power 3. 10 to the power 3 means 1,000, right? And then the next line is 2. This 2 means that this value is 2,000. And then next is 4, which represents 4,000, and then so on and so forth. And the next one over here is 10 to the power 4, which means 10,000. And then over here, this 2 is 20,000. And so on and so forth. This is how you read the numbers on the x-axis, on your Reynolds number. The other term that you can find, you will see that on the very left-hand side of these graphs, you have your equation for laminar flow. And you can see the line for laminar flow is strictly linear, meaning that F for laminar flow only changes with the Reynolds number, as you can see in this equation. However, the lines for other pipes, for turbulent flow, as you can see over here, They are curved. Take a look at this line, for example. These lines are curved, right? Meaning that F changes with Reynolds number and also relative roughness, K sub S divided by D. Perfect. So now you have a general idea about the Moody diagram. We're going to talk about it more, but first, let's go over two small examples of Moody diagram in next slide. One question that you might have right now is, how do we find the value of K sub S, or the equivalent sand roughness? So the answer to that is easy. There are different tables in the literature. For example, this table is from your textbook that lists different boundary materials or pipe materials and K sub S in millimeters or inches. For example, if you have a glass or plastic pipe, then your pipe is smooth. K sub S is going to be very, very small. However, if you have a concrete pipe, then your K sub S is going to be pretty significantly large. And it makes sense, right? Because concrete pipe is way rougher than a glass or plastic pipe. So when you find K sub S based on the material of your pipe, you can put it in this equation, K sub S over D, to be able to find relative roughness, and you can find relative roughness on Moody diagram. So in this example, we are going to find friction factor based on the given information, the given situation. Let's first talk about this situation over here. I'm going to call it example 1. We are going to find Reynolds, we're going to find F based on the given Reynolds number and the given K sub S over D. So whenever you have this kind of situation, the first thing that you need to do is to find K sub S over D. The K sub S over D is 0.002, and it can be located exactly over here, right? Now, you need to work with that line that represents that K sub S over D. That line is this line that I'm going over right now. Perfect. Now, the next thing that you need to do is to find Reynolds number. Reynolds number is 2 times 10 to the power 4. First, find 10 to the power 4. Here is 10 to the power 4, and then find 2 here. So this is the line. Go up until it crosses the green line again. It would be over here. So this is the point that I'm looking for. And then extend that to the y-axis to find friction factor associated with that Reynolds number and K sub S over D. So I can now tell that my friction factor is equal to 0.030. Perfect. Now, let's talk about another situation that we have over here. I'm going to call it situation number 2, or example number 2. We have Reynolds number and we had K sub S. We want to find F. Now, if you take a look at your K sub S divided by D, or relative roughness, it is 0.00015. But we don't have it on our y-axis. We have this value, which is 0.0002, and this value, which is 0.0001. The value that we have been given is something in between the two. So what I'm going to do is to have both of these lines in mind. So this one, and then this one. These are the two lines that I'm interested in, okay? Now, next, find your Reynolds number. Reynolds number would be 3 times 10 to the power 5. So first I'm going to find 10 to the power 5, and then 5 3. It would be over here. And then I'm going to go up until the line crosses my two considered lines. I'm going to go up like this. Perfect. So it crosses the upper line over here and the lower line over here. So I am going to continue that. And continue this one as well. Perfect. So now take a look at this one over here. The upper line over here. So how many divisions do we have between the two main divisions? This is 0.015, and then 16, 17, 18, 19, 20, right? So this line represents 0.016, and the top line represents 0.017. So our value, it would be something in between them. I'm going to conclude that F for me would be summation of those divided by 2, which is 0.0165. And this is how you find F based on Reynolds number and based on relative roughness.